Today, we are starting the next topic in the course, which is about the next powerful class of languages in the Chomsky classification, namely context-free languages. We learned about regular languages, their equivalent representations, properties. We learned about non-regularity and applications of regular languages. Similarly, about context-free languages also, we shall learn about two types of context-free languages, which are deterministic and non-deterministic context-free languages, and we shall learn about their representations: context-free grammar, push-down automaton, both deterministic and non-deterministic. Then we shall also see some applications of context-free languages and also proof that there are languages which are non-context free. And we can prove that every regular language is a context-free language. That is, context-free languages forms a family of languages more powerful than regular languages. To start with, we can discuss about grammar representation of context-free languages, and that is the agenda for today. We shall discuss about the basis for context-free grammars. I hope that you remember the basics of regular grammars that we already covered. If you have any difficulty in following this lecture, you please go back and see the lecture where we discussed about regular grammars. So the topic for today is an introduction to context-free grammars. Before we see an example context-free grammar, let us see why one should study context-free grammars. They are widely used in programming languages. For example, if you look at any high-level programming language, the language syntax is specified using context-free grammars. And the syntax analysis, which is called parsing, is actually an automaton processing that program based on a context-free grammar. And the automaton is nothing but a push-down automaton. And context-free grammars characterize languages accepted by a class of automata known as push-down automata, which can model programs with procedural calls. So you can have an automaton modeling a program which makes procedure calls. It can also model other infinite state systems, more powerful than finite state automata. And CFGs context-free grammars enable us to get easier proof for push-down languages. So that is another advantage of having context-free grammars, that they make proofs easy about some results on context-free languages. With this motivation, let us look at the first example context-free grammar. We can look at a few examples before we formally define what a context-free grammar is. Here is the first example. Consider the grammar G with the following two productions or rules. I hope you remember what are productions from the regular grammar. Even otherwise it's okay because we can see what it is. Now let us see how can you generate or derive a string in the language known as a sentence using the grammar. If you recall from the lecture on regular grammars, we saw that the process of generating a string in the language represented by the grammar, which is known as derivation process, which begins with the start symbol capital S. So there must be a start symbol in this case as well, this S. It must start with S, and it keeps rewriting sentential form, which are nothing but the current string. To start with, just S is the current string. Then you replace that S, which is known as a non-terminal represented by a capital letter. You replace a non-terminal, which is a capital letter, by the RHS of a production in which the symbol that you are rewriting is the LHS. Application on this grammar or derivation with this example grammar will make it more clear. Let us proceed. We can look at example derivations. So, as per this rule, you should start with the start symbol of this grammar, which is S. Then you can replace S with one of the productions in which S is the LHS. So, in this case there are two. If you apply production number 2, you can replace capital S with epsilon, then you are getting just epsilon, which is a string, which is the empty string. So, you can say that from the start symbol S, you derived epsilon in one step, which is an element of the language. Second example derivation, you start with S, always you have to start with S. Now apply production number 1. You can replace this S with the RHS of this production, you are getting this. Now on this, you can apply production number 1 or 2. If you apply production number 2, you are replacing S with epsilon, so you are getting the terminal string AB, which is also in the language. So if you derive a string of small letters or called terminals, which is a string in the language, and this is the process of deriving that. So you can say that you derived the sentence or string in the language AB using two steps in the derivation from the start symbol. Third example derivation, you apply production number 1, then again you apply the same production. So here you are replacing S with ASB. In this case, this middle S is replaced with ASB. Then apply production number 2, you will get BB in the language, A square B square. So you can say that in 3 steps you derived ABB or A square B square. Now with this, can you generalize and guess what language is represented by this grammar? It's not difficult to generalize it as this language. You can in fact derive any string of the form a to the power n, b to the power n. When you substitute n as 0, you are getting epsilon. N as 1, this. N as 2, you will get this string. So depending on how many times you are applying production number 1 before you apply production number 2, you can generate any string. So that is a language which is not to be a non-regular language, which is proved to be a non-regular language, and now you are getting a formal representation for a non-regular language, which is a context-free grammar. And given this grammar, it can also be represented like this. If you have more than one production for the same symbol, you can combine them like this, meaning there are 2 productions for S, one is this and the other one is epsilon, separated with a pipe character. This is another representation. Now let us look at another example context free grammar. Please don't get worried about this. We can try deriving strings. You start with the start simple, apply protection number 5, you are deriving epsilon in one step. Next example, you start with S, now applying protection number 3, you are getting a terminal string A derived in one step. So these are in the language. Then I am applying protection number 4, I can derive the terminal string B in one step. Then if I apply protection number 1, I will get this. Then on this capital S, apply protection number 5, I will get AA, which is in the language. Now let us look at the next example. You apply protection number 2, you are getting this. Then on this capital S, apply protection number 5, you are getting BB in 2 steps. Now try applying protection number 1, you are getting this. Then on this capital S, you apply protection number 4. So you are replacing capital S with B, you are getting ABA in 2 steps. Next example, if you apply protection number 2 to begin with, you are getting this. Then apply protection number 1, one is ASA, so you are replacing the middle S with ASA, you are getting this. Now if you apply protection number 4, what you do is you replace this S with a B, you are getting BABAB. So you can say that in 3 steps you are deriving BABAB. It's not very easy to guess the language, but can you guess? If you are not able to guess, then go for more and more strings derived. Observe what are all the strings in the language, then make a wide guess what the language is. Here you can prove that the language is the set of all palindromes or the set of all strings of the form W such that W is same as the reverse of W. You see that if you read from the left or right, you are getting the same string, so it is the set of all palindromes. This is also a non-regular language for which you are getting a context free grammar. Now you may be worrying about how can I get the language, that you have to keep on trying generating strings and then generalize and say what the language is. And once you guess that this is the language, you definitely have to prove it. That we shall consider in the next lecture, how to prove that a language is, a grammar is generating a particular language. Now proceeding to the next example, I am giving you a grammar. Again, don't worry about what these protections are. Let us try generating strings and generalize and see what the language is. You start with S. If I apply protection number 4, no doubt in one step null string is derived. Then I apply protection number 1. Yes, this is what I am getting. Then on the capital S, I am applying protection number 4. I am deriving AB in 2 steps. Then starting with 2, this is the protection I applied. On this S, apply protection number 4. I am getting BA. Then as the first step, apply protection number 1. Second step, protection number 2. So in this case, capital S is replaced with BSA. And then apply protection number 4, I am getting ABAB in 3 steps. Then start with 3, which is SS, then apply protection number 1. On the first S, I am getting ASB in that place. Then you apply protection number 4 on the first S, here you are getting AB here followed by this S. Then apply protection number 2 on this S, now I am getting BSA replacing this capital S. And on applying protection number 4, I will get ABBA. In how many steps? In 5 steps. Here again you may want to derive more sentences or strings in the language to guess what that language is. That you may try offline, but with these 5 strings, can you guess what kind of a language it is representing. You look at all these strings derived, can you find a pattern or a property which all these strings satisfies, then try to guess the language, and later you have to prove. You can verify that it is the set of all strings over AB with equal number of A's and B's. Here A's and B's equal number 0, 1, 2, here again 1 A and 1 B, 2 A's and 2 B's, here again 2 A's and 2 B's. In fact, you can prove that this is generating precisely the set of all strings over AB with equal number of A's and B's. This is again not to be a non-regular language, but we have a context-free grammar. Now we have enough examples. We can try to formally define what a context-free grammar is. Recall the first example and try to see which are all the components in it. And the definition is actually very similar to the definition of the regular grammar. The only difference is in the structure of the productions or rule. That is the only difference. Otherwise, just the context-free grammar with some more flexibility in productions. So we have a grammar which is a quadruple, a set of variables. You can see a set of finite set of variables or non-terminal symbols, which is represented by V, and in this case only one, capital S, which are generally represented by capital letters. In our course, we will only use capital letters to represent variables, finite. Then the set of terminal symbols, capital T, again a finite set, in this case small a and small b. When compared to automata, this is the alphabet set. Here it is called the terminals, set of terminal symbols, a finite set. Then as the third thing, you have one of the variable designated as the start symbol, which is an element of the variable set designated as the start symbol. In this case, only one variable, which is the start symbol. And whenever possible, we can use capital S as the start symbol. You are free to use any variable, but maybe S is more easy to make the grammar readable. And finally, finite set of productions. Here two productions are there, and each production is of the form alpha can be replaced with beta, where alpha is a variable. So the LHS is a variable, same as that of the regular grammar, and the RHS can be any string of variables and terminals. Here you have a flexibility. If you recall, in the case of a regular grammar, the RHS can contain at most one variable, and it must be the rightmost variable in all the productions or the leftmost variable in all the productions. That is what we learned. But here we have flexibility. The RHS can be any string of variables and non-terminals. Variables and terminals. Variables are called non-terminals. So it can be any string of variables or terminal symbols. And that is the flexibility which enables us to have context-free grammar for languages which are non-regular, because regular grammar is more restricted. In the RHS, you can have at most one variable, and that must be the rightmost or the leftmost in all productions. I hope you remember that definition. And now let us proceed and see what language is represented by a context-free grammar. For that, let us look at this notation. This represents the fact that we can derive the string W from the start symbol S of the grammar G using 0 or more steps in the derivation. this is the notation, but you have to do at least one derivation, but star stands for 0 or more steps, that is deriving the string W from the start simple S of the grammar G by using 0 or more steps in the derivation, that is the notation. And with this notation we can define the language represented by a context free grammar. Here is how you can define. The language L of G represented by context free grammar G with this as the set of variables or non-terminals, set of terminals, start simple and productions. It is represented as the set of all terminal strings W such that W can be derived from the start simple of G using 0 or more steps in the derivation. It is the set of all strings which you can derive from the start simple. And a language is said to be a context free language if there exists a context free grammar G such that the language is generated by that grammar. If that language is the language represented by a context free grammar, then the language is called context free. That is, a language is context free if there exists a context free grammar generating that language. So, if you want to prove that a language is context free, then you can just come up with a context free grammar representing that language. That's enough. With this, we are coming to the last slide where I am giving you two exercise questions for you to practice and understand how can you get context free grammars for representing languages, and thus how can you prove that certain languages are context free. First language where you have m number of A's followed by n number of B's, where m is greater than n, which is not to be a non-regular language. And here it is m number of A's followed by n number of B's followed by m plus n number of C's. This is again a non-regular language, but you can get a context free grammar and thus conclude that it's a context free language. Today we have seen context free grammars which are mathematical representations or formal representation for what are called context free languages. And if you recall the definition of the context free grammar, we saw that it's very similar to the definition of regular grammar, where the only difference is in the structure of productions. In the case of context free grammars, the structure is more relaxed. For a regular grammar, the LHS is a variable, and for context free grammar also LHS is a variable, no difference in the LHS. But for a context free grammar, the RHS of a production can be any string of terminals and variables. But in the case of regular grammar, it is restricted. The RHS can contain at most one variable, and that variable must be the rightmost variable in all the productions or the leftmost variable in all the productions. So, you can easily see that every regular grammar is also a context free grammar because the RHS is a string of variables and terminals. Thus, every regular grammar is also a context free grammar, and hence we can conclude that every regular language is also a context free language. With this, we are finishing this lecture. In the next lecture, we can see how we can prove the correctness of the language represented by a context free grammar, which is using the principle of mathematical induction, and that we shall see in the next lecture. Thank you.